Guess let's get started then. Well, welcome everyone to today's OVTO webinar. It's great to have you join us today for the session on ARCGen. We are pleased to have Devin Hartland, the developer of ARCGen, which is available as MATLAB and Python libraries. He will be walking us through the principles behind ARCGen today and also have a practical demo of the tool. OVTO Webinars is a new initiative from OVTO, the Open Virtual Testing Organization. You may not have previously heard about OVTO. Some of you may be familiar with the OpenVT platform, which is a platform that hosts collaborative repositories, open source models and initiatives like Viva Plus, human body models, HBM4VT, and more recently, pre-crash tools are hosted on the OpenVT platform. In line with OVTO's goals to support open science, OVTO webinar intends to serve as a platform to highlight efforts in this area of road safety, and also to serve as a meeting place to disseminate knowledge that we need to foster virtual testing. Before Devin starts, some housekeeping for us today. You will know when you have registered that this meeting is being recorded and will be available online later. So please keep your microphones muted during the presentation. We will have a time for discussion in the end when you could use the raise hand feature in WebEx to talk to Devin. That's it from me. Devin, tell us about ARCGen.
Absolutely. So let me share my screen. All right, we're good?
Looks good, yes.
Excellent. All right, good day, everyone, and thank you for inviting me to the OVTO webinar series. So my name is Devin Hartland. I just completed my PhD in mechanical engineering at the University of Waterloo under Dwayne Cronin. In fact, my convocation is tomorrow night, so it's been a bit of a busy week this week. So my background is actually in a lot of materials testing and component testing, not just in sort of the
Is it just me who cannot hear Devon?
Can you? Sorry, Johan.
Yeah, I can hear you okay, Devin.
You can hear me okay? Okay, sorry, Johan. It seems like it might just be you. All right. So, but if there's anyone else in the audience who is not able to hear me, please let me know. All right. So my background is materials and component testing as well as signal processing, and I'm also the co-founder of Arcus Analytica, which I'm going to touch on a bit later in this presentation. In this webinar, I'm going to begin with an introduction of ARCGen and sort of the arc length analysis framework which powers it. I'm going to give you a demonstration of how to use ARCGen with some real data in real time, and then give you sort of my outlook and upcoming work on some of the really cool applications of ARCGen and the arc length analysis framework. And hopefully we'll have some questions. So diving into things, I think everyone in the audience can agree that one of the biggest challenges we face in biomechanics, and especially for challenges like virtual testing, is that we're dealing with a hugely varied and variable type of signals in biomechanics. And we really need to deal with all of them. Things such as material response, which might be monotonic in nature, but not terminate at the same point in the x-axis. Things like time series data, whether that's head accelerations or some other kinematics we're tracking from an experiment. This is data that exists sort of along a similar time frame, for example, 0 to 300 milliseconds, but might not necessarily be well aligned in terms of features. And finally, we have this really old historic data that is incredibly valuable for validating HBMs and ATDs, but is really hard to deal with because it is non-monotonic and hysteretic. And the big question we have for a lot of open virtual testing, particularly for developing models and surrogates, is how do we actually use this data? And that's where ARCGen steps in. The idea is that we take this experimental data and we reduce it to a single average and corridors. The problem is there isn't a general method that works across all these types of data. If the signals don't exist in all the same points in the x-axis, we have difficulty trying to actually compute an average response, let alone variability. For time series data, we might be able to do point-wise averaging, but rarely do we have data that is as well behaved as the NDBL dataset shown here. And finally, for this hysteretic dataset, there really hasn't been a lot of generally applicable methods. And historically, I put it in quotes, but eyeball average was actually found in a paper in the 1970s. And of course, being that subjective, it has no statistical foundation. And so into this is where I helped develop ARCGen. And ARCGen is based on the arc length analysis framework. Now, for those people who might not be aware, arc length is an intrinsic property of a curve that is basically just the length of the curve as we walk along it. And the advantage is it's always going to be monotonic. The length of the curve is always going to increase as we walk along it. And the arc length analysis framework is based on two components. The first in the upper right-hand corner is arc length reparameterization, where we monotonically resample all responses or signals based on the length of the curve. The second, and in my opinion, sort of the secret sauce to the entire thing, is signal registration, which allows us to align features across a family of signals to prevent distortion and enable feature-based analysis. The advantages of the arc length analysis framework is it is a consistent general methodology that works across a wide array of signal types, and it provides feature-based analysis. And from this, we developed ARCGen, which really, it was an acronym at one point. It's just a name now, but it provides feature-based averaging and corridors. Myself and my supervisor, Dwayne Cronin, published this in 2002 in Frontiers, and as we'll see later, we released open source MATLAB and Python software for you guys to use. So with that sort of introduction, I'm going to jump into actually how the arc length analysis framework and ARCGen work. And because I'm a very visual person, I've sort of developed a series of graphical animations to help show this along. Because it's being transmitted through the web, it might not look as smooth as it does on my screen, but my apologies if that's the case. So the arc length analysis framework begins with arc length reparameterization. And the advantage of this technique is it works on a wide array of signal types, regardless of the shape, termination, or number of points. So we can have data such as this, time series data, or even weird hysteretic data, such as the load-unload data I showed earlier. But let's go back to this initial set of data. We have three peaks that are relatively well aligned with respect to time. We have three signals that do not terminate at the same point, and we have this shared feature of a valley and a peak before decreasing again. That's not particularly well aligned in the x-axis. The first step of the arc length reparameterization is to scale all signals by the mean bounding box to eliminate magnitude differences between the axes. This is because if my y-axis, for example, was multiple orders of magnitude bigger than my x-axis, calculating arc length would sort of bias things towards the y-axis, and we would not actually have a shape-preserving measure. These normalized axes, these x hat and y hat, are only used for the arc length calculation. They're not used for any statistical analysis that follows. Once we've scaled things, we calculate the arc length of each signal. Then we normalize it by the length of each signal. This gives us this parameter s hat that varies uniformly between 0 and 1 for all signals. Because we have this uniform sampling variable, we can then resample all our signals with respect to normalized arc length s hat. Now we have x and y uniquely defined along a shared sampling variable of s hat between 0 and 1. They contain the same number of points and allows us to do analysis much simpler. Now, one of the underlying assumptions between arc length normalization is that shared features occur at similar normalized arc lengths, but we should always explore if our assumptions are true. So let's look at this more closely by looking at the y with respect to s hat in the lower corner. And we'll consider the first peak, which occurs around a normalized arc length of 0.45. If we zoom in and draw points at 0.45, we'll see that the peaks are pretty well aligned with respect to arc length, and the resulting average drawn with respect to arc length captures the peak location and magnitude well. But let's look at another example. Let's zoom in on an arc length of 0.75. Here, we have a case of a peak, a valley, and something in between. And if we draw an average through this with respect to arc length, we actually completely smear out that shared feature, which is not ideal. All of these signals share a valley, a valley, and a peak. We would expect the average response to also share that. This isn't just a problem shared by arc length reparameterization. It's a problem shared by a lot of pointwise averaging techniques because of variability between signals. This can come from intrinsic population variability between signals. Oscillatory behavior is often a driver of it, as well as signal noise. The question I have, though, is can we accommodate for variation in feature location? And the answer is yes, with signal registration. So the idea behind signal registration, and we're going to discuss this more, is we introduce warping functions, HFS, for each signal. These warping functions shift the arc length assigned with features in each signal. This warping process is entirely automatic, and it aims to maximize correlation between the x-axis with respect to normalized arc length and the y-axis with respect to normalized arc length. And if you sort of miss what's going on, we're going to go into more detail in a moment. But the advantage is when we draw an average response in black through our signals, we actually are capturing the true underlying shape of the signals. We're adjusting the arc length assigned to common features, not the actual XY location. So the signal registration step, and in particular the idea of warping signals, is generally pretty counterintuitive and it's not easy to visualize. So let's look at a closer look with a much simpler example. Let's consider this case where I have a number line between 0 and 10, and on that number line I have 11 circles numbered 0 to 10. The circle's number maps onto the initial position on the number line, and when I plot this, I get the gray curve on the right-hand side. This gray curve is, in fact, a warping function. It plots current location versus original location. So, with signal registration, I actually end up shifting where those circles occur on the number line, and I end up with a different warping function, which is shown in gold here. So, for example, if I'm looking at the circle at position 1 initially, so this guy, my current location is around 1.75. It's important to note that while the location of the circle has changed, the value has not. This is critical because it allows us to keep the initial shape of the function. So let's explore what signal registration looks like on real signals. So we're going to go back to our initial set of signals in the XY space, and we're going to focus on that area around that second peak and that valley. If we zoom in and we add our arc length of 0.75, we can see that we have this peak, this valley, and this somewhere in between. And as we had shown earlier, if we draw an average through this, we're going to completely distort that shared feature among all three signals. But introducing warping, or signal registration, allows us to align these features based on arc length. You can see the black circles are moving the arc length assigned to the peak. We're not actually changing the coordinates of that peak. It's this property that allows us to capture averages and responses, which are feature-based, and allows us to do really cool feature-based assessment in some future work we're going to discuss later in this presentation. So once we have everything reparameterized and registered with respect to normalized and warped arc length, we can begin calculating our average response and corridors. And this is the part that is sort of ties directly into ARCGen, or the outputs from ARCGen rather. So we have the mean response and standard deviation at each normalized arc length in X and Y, and those are denoted by the dots and error bars on the left-hand side. We can take these dots and error bars from the left-hand side and transfer them into the XY space for every normalized arc length. From here, our average response is drawn through each point in the XY curve, because it's important to notice that while I have 4 points shown here, there may actually be hundreds of points in my reparameterized signal. So we're able to get a smooth curve out. The corridors are a little bit trickier. As you can see on this slide, we have two-dimensional error bars showing variability in the Y and the X axes. Now, to represent this continuously, we're going to treat those error bars as 2D normal distributions, which are actually represented as ellipses in the X and Y axes. It's also important to realize that we have potentially hundreds of these ellipses along that average response. So we define the corridors as the envelope of all ellipses of variability. And we can draw that envelope numerically. So overall, this arc length analysis framework in ARCGen provides a consistent methodology for a robust, consistent, and feature-based assessment of average response and variability, applicable across the wide range of signal types we see in biomechanics and beyond. So with that, let's get into some actual applications of ARCGen before we get to the demo. And we'll begin with something fairly simple. This is stress-strain responses from porcine brain tissue, and this data was collected by one of my colleagues here at the University, Dilver Singh, earlier 2019. And this is compressive behavior of porcine brain tissue that was tested fresh and after being stored at room temperature for 24 and 48 hours to determine the effect that sort of dwell time, I guess, has on the material's behavior. These signals are all monotonic, but they terminate at different strains, which you can really see clearly in the blue signals. Now, this termination at different levels of strain makes it actually challenging to do things like pointwise averaging and standard deviations, so much so that the original data looked at computing, sort of cropping this data down to the earliest strain, and then doing a fairly simple pointwise average and standard deviation. That's not intended to be criticism. That's sort of just the only technology we had at the time in 2019. But with ARCGen, we're able to take all of those signals, feed them directly into ARCGen, and capture an average response, which is shown in the solid line, and corridors, which are shown by the shaded balloon, for all of the responses without any a priori knowledge of what those signals look like, or without worrying about where they end in time. Because the important thing is the ARCGen corridors capture variability, not just in stress, which is vertically, but also in strain, which is the horizontal component here. These corridors are also useful for qualitatively highlighting differences between conditions. We can see that perhaps there isn't a huge difference between tissues tested fresh and at 4 to 24 hours, but there's definitely a big difference between tissues tested fresh and after 48 hours. But it's important to note that this is not a strict statistical test. It's only a qualitative assessment, although I want to discuss some new tools that we're working on later in the presentation that help solve some of these problems. A more challenging application is a really influential data set in biomechanics, which is the Viano lateral thoracic impact test. And you have an example of it down here where postmortem human subjects were impacted laterally with a pendulum at 3 different velocities. And this has been highly influential for developing ATDs and human body models. The challenge with this data set and any sort of load-unload data is that it is hysteretic. That is, it is non-monotonic in both axes. And also because we're dealing with humans, it's highly variable. To develop corridors historically, there's been a number of different options. Viano et al. Published the maximum signal extents as the corridors, which you can see on the right-hand side here, which is basically just the outer envelope of all possible signals. This kind of works well to capture sort of an extreme degree of variability, but it lacks a certain degree of statistical rigor, and it's highly influenced by outliers and extreme behavior. And calculating an average is even another challenge, where no average was actually reported with this data. And as I'd mentioned earlier, contemporaneous work will often use an eyeball average, or a subject matter expert going in and drawing the average by hand. Generally, they are quite close, and it's been remarkable to see how close these eyeball averages fall to the ARCGen response. But it's always good to have a general methodology that works to all of these signals. And there has been some work, such as work by Dave Leslie, which requires manual segmentation of the signals. But the advantage of ARCGen is really that we can take all of these responses, feed them into ARCGen, and produce an average response and corridors that captures the underlying shape of the response, regardless of whether it's hysteretic or not. Here, we're capturing the peaks, the sort of plateau phase in the response, and the unload behavior. And the corridors are based on standard deviation, not extreme bounds. This makes them less prone to outliers. A good example of this is actually the blue curves at the bottom. It might be a little unclear, so I'll jump back 2 slides. But you can see in the blue curves, we had this major outlier that was sort of a prominent outlier in the responses. With traditional corridor techniques, such as the one shown on this slide, that would make for some funny looking corridors. But with ARCGen, we're able to mitigate the effect of that. The average response still falls within the average of the signals, as we'd expect. It's just that the corridors look a little more ballooned than we'd expect. The big thing is, though, we don't need manual processing or segmentation to deal with these challenging data sets. We can just feed them into ARCGen and have a good response. So with that, let's actually dive into some real data sets with ARCGen. And I'm going to swap over to MATLAB. In this data set, we're going to be working with the NVDL, or Naval Biodynamics Laboratory data set, which is available from the NHTSA crash database, or data, I can't remember what it's called, apologies. But this consists of volunteers strapped into an acceleration sled and subjected to oblique impact pulses, or rather acceleration pulses at varying severities. So let's bring up MATLAB and load the database. So this is what our signals are going to look like. On the right here, we have, this is going to be y-angular acceleration of the head. So the head in the y-angular direction, this is the nodding direction, forward and backward. So what we can see here is we have 8 signals rather. And we have them all as sort of typical of the NBDL dataset. They're all very well aligned in time. So we have an initial peak around 120 milliseconds, and we have sort of this decrease, plateau, and another decrease around 190 milliseconds in time before going back to about 0. There are some exceptions though. We have this yellow curve, which is a fairly prominent outlier in how high the initial acceleration goes, and it doesn't show the same acceleration response in the trough or the valley. Additionally, we have curves like this green curve in the background, which doesn't show this initial hump that many of the other curves show, as well as the unload behavior is quite steep and much more flat than we'd see in something like the orange or blue curves here. So this is the data set that we're going to play with because it's really useful for demonstrating a number of core principles of ARCGen, particularly how signal registration is controlled and set. So again, I'm using MATLAB here just because it's going to be more useful for giving interactive demos, but everything I present here can be used in the Python version as well. The only difference between the two versions is the input format required for the function. In MATLAB, there we go. In MATLAB, the input data has to be in a certain format for ARCGen to work, and that is a structured array. These structured arrays, if you're used to MATLAB or have not been exposed to them, they're actually super useful for writing really nice readable code. But they basically work as rows which are numbered, and the columns are actually named, and you access them with a dot index. For MATLAB ARCGen, you need one column called data, and an optional column called spec ID or specimen ID. This allows us to sort of name each specimen, and this is where we have our input data. And the input data is a 2-column array with X and Y points. If you're using Python, the input is actually going to be a list of ND arrays, and there isn't the option to put in a specimen ID for each column or for each signal. So I've shown you what the signals look like. Let's get down to actually calling ARCGen. So for this demonstration, I have called out, and let me zoom in, yes, because I can do that with the new MATLAB. I have defined 4 important ARCGen parameters. They are the number of resampling points. That's the number of points which the final curve will have, which is not necessarily the same as the points going in. The corridor grid points, that is something we're going to discuss more because it's a little bit subtle. The number of warping points, which in my opinion is probably the most important response in ARCGen, and a warping penalty factor. And the reason I define these here is just so they're easy to change for the demo. So I'm going to uncomment what the ARCGen function call looks like. And this function call should have the same signature whether you're in MATLAB or Python, although there might be some minor differences. So basically, it is a single function called ARCGen that you're able to call, and you input your input signals. Again, that is your structured array in MATLAB, or it's your list of ND arrays or NumPy arrays in Python. And if you ever want more information on how ARCGen works, if it's installed in MATLAB, you can just open it up, and it should just pop up, and you have all the documentation we provide for ARCGen. So we have sort of an introduction of what it does, but I think most of you guys would be interested in the format for the mandatory inputs and a description of all the optional inputs for MATLAB. And we're actually going to discuss some of those optional inputs during this presentation. So we have ARCGen, we have our input signals, we have our number of resample points, our corridor resolution, our number of warping points, and our warping penalty, all defined above. MATLAB also has the ability to do parallel processing to accelerate things if you have the parallel computing toolbox. The outputs from ARCGen are there's 5 outputs. There's the average response, there's the inner and outer corridor. All 3 of these are 2-column arrays describing XY points. For those of you familiar with corridors, you might be more familiar with an upper and a lower corridor. The reason why we're using the term inner and outer is because upper and lower doesn't really make a whole lot of sense when you have a curve that loops back on itself. We have processed signals, which is all the signals that are processed during the ARCGen process that are output for you to view. And we have some debug data, which is useful if you want to extract out the standard deviation at each point in the average response. So with that, you can actually just run ARCGen. So what I'm going to do is I'm uncommenting a bunch of code that is basically just going to plot our initial signals in gray, plot our average response in black, and then plot our corridors in gold. And we have our average response ARCGen average shown here. And I want to emphasize that right now we have the number of warping points set to 0, which is not a condition that I'm going to recommend people use ARCGen in. The signal registration is really important to getting good quality results, especially for data that is not as well behaved as the NBDL dataset. But even without signal registration, the average response is capturing the underlying behavior pretty well. We're capturing an initial peak here. We're capturing sort of a decrease. We're not really capturing a plateau, but we're capturing the average valley here and this behavior out here. But I think we can do better because we're not capturing this initial hump and valley, and we're not capturing the plateau here. And the reason for that is we're not applying signal registration to align features with respect to normalized arc length. So we're going to go back to our function call in ARCGen, and I'm going to add another parameter. And that parameter is called diagnostics. I'm going to set it to on and run it again. And what diagnostics is going to do is it's going to create another plot over here. It's going to create 4 plots, in fact. We have our reparameterized signals in the upper right-hand corner, our warping functions, which we don't have yet, but pressing it to this discussion is the average and standard deviation with respect to x on the left and y on the right. Now this data is monotonic and continuously sampled at x, so the x data is not as useful for us, but the y data is very useful for us. And as you can see down here, we're not really aligning features with respect to normalized arc length. This blue curve, for instance, the peak is way out here when we'd expect it to be back here. And especially when we're looking at the valley down here, the valleys for all the responses are not well aligned. This is where signal registration comes into play, aligning features with respect to this normalized arc length parameter without changing the XY coordinates of that data. So let's add some warping points. So the guidance that I provide for warping points is it is unfortunately a user-defined parameter. I always recommend at least 1 warping point, and then I recommend the number of prominent shared features in your response. So across all these responses, we have sort of a big valley, which would be 1, a big peak, which would be 1, and then a second valley or negative peak, which would be another. We also have this plateau phase, which I think would probably also be a shared feature I'd like to capture. So I'm going to put in 3 warping points, and we're going to see how the average and corridors change with that. So I'm going to make sure I'm not turning off my plots. And I'm going to increase my number of warping points here to 3 and run it. Now this is going to take a little bit longer because the signal registration process can take a bit of time. In MATLAB, we're taking advantage of parallel processing, which speeds things up a lot. The Python package doesn't have parallel processing, I'm afraid. But we have our average response and corridor shown here. And if I drag sort of the warping points with 3 over to the left, and we look at the one with 0 on the right, and on the left we have 0, you can see there's actually, it's fairly subtle, but it's an important change to our average responses. The average response with 3 warping points captures the peak a little bit better. It's capturing where this outlier is occurring for sure. It's capturing this rise of the initial bit of data and little fall, which occurs in most of our signals. We're capturing this decrease and then this plateau, which again was shared in most of our features, as well as the valley here before rising to 0 acceleration. So this is really important for capturing responses that may not be well aligned with respect to time, or responses that may be sort of shifted in the XY space. Again, this example is perhaps not the best for demonstrating misaligned features because the NBDL dataset is remarkably well aligned. But I think it's a useful demonstration. Now you might ask, well, what if we add more warping points? So I can go back to my dataset and increase this to 5. just as a demonstration. And what you'll notice when this runs, and it's going to take longer because there's more parameters that need to be optimized to align signals, is when we have 5 warping points over on the left-hand side, and I'm going to drag this guy over here, which is 3 warping points. There isn't a huge difference between the two. Perhaps we're capturing a little more of the reversal down here around 150 milliseconds, but overall, we're capturing the response the same as 3. And this is pretty typical. The more we explore this tool, the more we're seeing that there tends to be convergent behavior with the number of warping points, which is fine, and it's pretty good. The other thing I'll note, though, is if you look here at the beginning of the data, the gold corridors do not extend all the way to the beginning. And this will particularly show up if you have data that is like perfectly 0 for a period of time. ARCGen cannot really enhance or extend corridors out that far manually. And the reason for that is I'm actually going to bring up another diagnostic plot. In my diagnostics option here, I'm going to change this to detailed. And this is going to create a plot that's a little bit hard to visualize, but it sort of follows the plots that I had shown in the presentation earlier. All right, detailed ellipses. So what we're looking at here is a little bit busy, but I'm going to zoom in on the average response. The black curve is the average response, and the dots are all the points in the average response. And these gray ellipses are the ellipses of uncertainty we have at every single point. The corridors from ARCGen are extracted numerically. I'm using a numerical algorithm to try and find the edge of all these ellipses. So if my ellipses are not overlapping, or if my ellipses are not super tight together, I will have these sort of bumpy artifacts you see in the blue curve here. Or I'll have behavior, such as out here, where my ellipses don't overlap at all, and I can't actually project an envelope into space that doesn't exist. Or there might be a way in the future, but it's not something that we wanted to do to screw with the data. But there are some options. The first option is to increase our corridor resolution here. So we can increase that to 500 points, and that's going to make a finer mesh that allows us to extract a more detailed resolution of those edges of the ellipses. The other thing we can do is increase our number of resample points. The input data in this case had 600 points, and I'm only resampling to 250, because that's the default in ARCGen. There's no reason for that default. It was just a value that I need to input. My recommendation is never resample more, or particularly much more, than the number of points you have in the initial set of signals, as then at that point you're sort of interpolating what's going on between signal points. But let's increase that to 500 and run it again. And this is going to take a little bit longer because there's more ellipses and there's more grid points, but it still should run fairly quickly for this example. And if we go back to this detailed debug plot, the two things I want to call out is this blue curve on either side is much more smooth. I'm sorry it was jerky there. And our corridors now extend a lot closer to 0 in time. The other option we have for this is sort of another bit of a numerical cheat, and that's an option called min corridor width. And what it does is it says any corridor that is less than 0.01 of the maximum standard deviation found in the entire range of responses will get scaled to this minimum corridor width. And this is useful if you have data that is like particularly 0 at all points, but you want to have a corridor that shows up visually if you're doing something like a corridor assessment with Cora or ISO later on, and you need an inner and outer corridor based on some value. And if we go down here and look at the beginning, we can see that we've sort of ballooned the size of the corridor artificially. It's important to note that adding this parameter may allow you to extend your corridors to the beginning of your data if you are not having that, but it does impact sort of the validity of what those corridors mean. This is not really one standard deviation anymore. But it would be useful for something like metrics, like the Cora metric or the ISO 18571 metric. So that's been a demonstration of ARCGen and sort of how ARCGen works in MATLAB. Everything I just presented will work in Python as well. Just the plotting I found was a little bit nicer in MATLAB for this presentation. So I'm going to jump back to my presentation, and we're going to talk about the upcoming work. And there's some really cool work that's being using ARCGen presently and things that we're developing under ARCGen. And I want to begin by the excellent work by Karina Klug's gang at TU Graz, which is really helping with the HBM4VT, or human body models, for virtual testing. The Euro NCAP CP550 technical bulletin focuses on presenting a roadmap for qualifying human body models for automotive occupant safety, with the goal of providing and ensuring that these human body models meet baseline requirements and ensure regulatory compliance. Now, my involvement with HBM4VT has been fairly peripheral, but ARCGen has been adopted for a number of options. As part of the HBM4VT program, Karina Klug's gang has developed and collected a whole lot of experimental data from historical tests and combined them together. And ARCGen has been used to develop averages and corridors from all this experimental data for qualification purposes. The other thing ARCGen has been used for is as a basis for developing methods to objectively rate human body model fits to experimental data. And from this, and this is work that's really spearheaded by Felix Rezi and Bernd Schneider at TU Graz, are two metrics that use arc length-based techniques derived from ARCGen. These techniques are called the ellipse score and dynamic arc length warping. I don't have a whole lot of time to get into exactly how they work, and I don't want to take away from the excellent work that Felix and Bernd have done in this work, but in general, these techniques are very similar to the corridor score you would have in Cora or in the ISO 18571 metric. You have an ARCGen average, which is shown in light blue here, and you have an experimental response, a model response, which is shown in the dark blue curve. You map the model response onto the ARCGen average, and for each point, you have two ellipses, one representing one standard deviation and one representing two standard deviations. And like a corridor score, if you're inside the inner ellipse, you get a score of 1 for that point. If you're outside the outer ellipse, you get a score of 0. And if you're in between, you get a score that varies between 0 and 1, depending on how close you are. Now, the advantage of the ellipse score and the dynamic arc length warping is that it's suitable to measure, it captures variability in both X and Y simultaneously. So we're capturing variability in both force and displacement, because a lot of the test data in the HBM4VT program is not necessarily time-based signals, where we have a known domain to evaluate things in. That allows us to be general across a number of signals, as well as being able to capture this multidimensional variability. So this work is being published, hopefully at ARCGen 2025 in a paper there. It's also published in, of course, the Euro NCAP CP550 technical bulletin, which you can find online. And like I said, my work in this project has been fairly peripheral to providing some guidance and asking a lot of hard questions for Felix and Bernd, but it's been a lot of fun. The people who have really spearheaded this work are Felix Rezi, Bernd Schneider, Desiree Koffler, Vishnavel Khan, and of course, Karina Klug at TU Graz. So work that I'm working on here at the University of Waterloo is actually extending ARCGen to provide answer more questions. And what we focused on was, how do we perform statistical analysis? Let's look at this example data set on the right-hand side here. It is sort of head rotation, or in the nodding direction, for the same oblique data set we had seen previously in the demonstration. We have a 9G pulse and a 7G pulse, and we want to ask the question, are these responses different? If we wanted to do a t-test or ANOVA, we have to extract out a scalar value. But what scalar do we extract? A peak value, a time to peak, a slope? How do we know that extracting out that value is not introducing bias? What if there's a way we could operate continuously on this data? We just input the data and we get out an answer. And the answer is, there is actually a technique out there called statistical parametric mapping, which was developed for neuroimaging, and some of you in the biomechanics community might be familiar with its adoption in gait analysis through the program SPM1D. The advantage of statistical parametric mapping, or SPM, is that it accounts for the correlation of neighboring points. So instead of having to run like 100 t-tests on all the points, which can introduce the multiple comparison problem, we account for that correlation. It not only tells us if a statistical difference exists, but it highlights the statistically different areas, such as the highlighted regions in the brain atlas, as shown on the bottom here. That means we don't need to extract those scalars, and we don't introduce regional bias. So if you'll permit me some time, I want to talk about how this technique works, because it's really cool. So we have two sets of responses here, in blue and in red, and they do not have a common termination point. Similarly, they have differences in the y-axis and the x-axis simultaneously. So the first step of this arc length-based statistical parametric mapping is to reparameterize and register everything with respect to normalized arc length. This is the same process I described earlier in the presentation, but it allows us to align features in the X and Y space with respect to arc length, and it provides a uniform sampling variable from 0 to 1 to operate on. Once we have reparameterized and registered everything, we compute what is known as a statistical map. The statistical map is created by calculating a test statistic at each point with respect to normalized arc length. Now, this test statistic must capture variability in the X and Y axis simultaneously. So we need a technique such as the hoteling t-squared test that we can see on the top here to capture that variability. This hoteling t-squared test can be thought of as just a multivariate extension of the t-test we're more familiar with in scalar testing. So this statistical map represents the variability between sets of responses across the entire range of response. From here, the process of conducting a statistical inference is actually analogous to scalar statistics. So let's discuss that briefly. With scalar statistics, we assume a probability distribution, and we calculate some test statistic based on that distribution, which in this case is shown in blue. Then, based on the distribution, variability, and number of repeats, we calculate some critical value, usually z crit. If our test statistic is greater than z crit, as it is in this case, we would say that the null hypothesis is rejected, and we can say a statistically significant difference exists. If there's some statisticians in the crowd, you'll know that I am being very general with my language. I apologize, it is more subtle than that, but I want the meaning to be made clear to sort of the general audience. Now, this is with scalar statistics. With SPM, it's actually the same, but instead of having these scalar probability distributions, we replace them with n-dimensional extensions with random field theory. Now, it's not a black box as shown on the screen, but it is incredibly hard to visualize n-dimensional random fields in a 2D medium such as this. Similarly, we're going to replace our mean and standard deviation with another parameter called full width at half maximum, which is equivalent for this multidimensional case. All of this data gets fed into random field theory, and we get out an SPM threshold that accounts for the correlation between neighboring points and eliminates the multiple comparison problem. We can take this threshold and apply it to our computed statistical parametric map, and we say that any region of the map above this threshold is statistically significant. And these are known as clusters of significance, defined with respect to normalized arc length. We can take our arc length and apply it to our X and Y data, shown here, defined with respect to normalized arc length. And we're capturing differences in the x-axis and the y-axis simultaneously from a single statistical map shown in the upper right left-hand corner. Now, this is shown in the sort of the arc length space. I think it's also useful to visualize it in the XY space. So I'm going to plot the average response and corridors for each of those sets of data, and the shaded regions in this diagram represent where those clusters of significance occur. They're not bounded by extents in either the X or Y axes, but rather with respect to this arc length. Finally, for interpretation, we'd say that if a cluster exists, the sets of responses are statistically different overall, and these clusters represent areas where random chance alone would not be likely to cause such a difference. Overall, this arc length-based SPM approach enables feature-based statistical analysis without the need to extract out scalar metrics. So let's look at an example where this case really shines. And we're going to go back to that 7 and 9G data case I showed previously. And again, this is from an oblique sled test from the NBDL dataset. And this is y-axis head rotation, or nodding of the head. And the question we ask is, are head rotations different for a significance of 0.05? If we perform a scalar t-test on peak values, we'd actually say that no significant difference exists because the peaks are close enough together. But we visually, like intuitively as engineers, would say there's likely a difference because the curves look different. And arc map, or this arc length-based SPM technique, really helps to highlight what we see as engineers. This grade cluster is highlighting where differences in timing and slope between our two sets of responses are driving differences. What's also interesting to note is we're not capturing differences in peak behavior. Rather, we're only capturing the differences in the slope or the rise behavior. So this technique, which I kind of alluded to, is called arc map. will hopefully be coming soon. We have a journal paper we've been working on for forever, but we're finally through the second round of revision, so hopefully that should be published in Annals shortly, fingers crossed. But a lot of this methodology and data has already been presented. So we presented this data set in particular at the GHBMC workshop last year in 2024, as well as a short com at ARCGen 2021 in Stockholm last September. So with that, I just want to sort of close up. In this presentation, you've seen ARCGen, and particularly the arc length analysis framework. And this framework is a consistently, widely applicable methodology that works across almost all the signals we see in biomechanics and hopefully beyond. The big advantages with ARCGen is not only that it is so consistent, but it captures multi-dimensional variability. We're also capturing feature-based assessment, not just for corridors, but also for statistical testing with feature techniques. I provided a demonstration of ARCGen, which is the free MATLAB and Python toolbox that we produced here to go along with our initial publication. And the advantage here is it computes feature-based averages and corridors that is widely applicable to all the range of signals in biomechanics. And it's been very humbling over the last about 3 years to see the wide adoption we've seen in the injury mechanics field and beyond. It's always fun to sort of see when a new citation pops up to see what new work is going on, and to meet people at conferences who are using my tool, and it's really cool. So if you think this work might work for you, we have a free MATLAB and Python toolbox, as I said. You can follow the QR code at the bottom or this link, github.com/immc-uwaterloo. And if you got nothing else out of the demo, it is please use signal registration. I get a lot of questions, people ask me why their results don't make sense. And the answer is almost always use signal registration. So I think there's some really interesting outlooks on where this arc length analysis framework can go. And that definitely starts with the Euro NCAP CP550 technical bulletin and arc length based model validation tools. This is actually really important, I think, for the OVTO, the OpenVT organization, because again, an important thing to virtual testing is ensuring that the virtual test matches reality. Here at Waterloo, we're working on arc length based statistical analysis, as well as trying to push the arc length analysis framework into new fields and new applications. I think there's a wide range of data types out there where this tool would be really useful. And to sort of maybe toot my own horn a little bit, one of the ways we're trying to advance that arc length analysis framework is through a new company I'm co-founding with my supervisor called Arcus Analytica. And our goal here is to advance the arc length analysis framework with rigorous supported software solutions. We get excellent feedback at conferences and workshops about using ARCGen, and the open source stuff is something I'm really passionate about. But when we talk to industry, they're often, let's say, hesitant to adopt open source software for a number of reasons, not the least being that it is not supported if something goes wrong. And the goal of Arcus Analytica is to really push that supported software to see more adoption of these tools in industry. Our first tool is going to be called ARCGen Plus, funny enough, and is going to combine all the powers of ARCGen with model validation techniques such as Cora, ISO, BioRank, and perhaps in the future, the Euro NCAP standards once those get nailed down, all in a single code-free software solution. We're trying to lower the barrier to entry to use ARCGen so you don't need to deal with learning how to use MATLAB or Python or dealing with library dependencies. Similarly, we're going to be working on a tool later, hopefully by the end of this year, called ARCSuite. That name is in the works, preferably. But the goal of that software is to provide interactive end-to-end data processing and analysis with a friendly graphical user interface. So again, that company is called Arcus Analytica. We will have a parked page going up soon at arcusanalytica.com if you're interested in learning more, or you can just contact me with the contact information on this screen. I want to thank you all for your attention today and acknowledge that work like this does have to have money coming from somewhere. In this case, it's the Natural Science and Engineering Research Council of Canada, as well as parts of my PhD research were funded through the Ontario Advanced Manufacturing Consortium. You have the link here to view ARCGen if you'd like. Once again, my name is Devin Hartland. I'm a research associate at the University of Waterloo with the Impact Mechanics and Material Characterization Group with Dwayne Cronin. And thank you for your time today.
Thank you. Thank you very much, Devin. That was a really nice talk. Nice demonstration there.
Yeah, sorry, I think I went a little bit long. I apologize, but we still have, I think, 7 or 8 minutes for questions.
Oh, Absolutely good. We already have questions coming in. Arne, do you want to go first?
Yeah, this is Arne Keller, Working Group on Accidents Mechanics Zurich. First, thank you very much for this very interesting talk, really great work, and a couple of really cool approaches in there. I was wondering, how do the average curves that you give, how do they compare to the field of curves in terms of similarity coefficients?
Like shape analysis kind of thing. That's something we're exploring currently. It's actually something we're looking at a lot for sort of finding ways to automate the warping process. So right now, I would say that's not something we have done a whole lot of, but we will try to be getting there.
Yeah. Because there is actually a way of deriving an average curve that maximizes the possible similarity. I've worked on that a little bit. Can give you a link to that if you like.
Yeah, there's some work. I absolutely agree. So I will first off preface this by saying the warping techniques that we have here, I would call them the 90% solution. It's always been the one thing I've been unhappy with ARCGen, in that it requires user-defined parameters. I am actually still investigating techniques to improve that. There's some work by a researcher called Tucker, I believe, which has some really cool techniques which provide a much more rigorous registration approach that doesn't have as many user-defined parameters. We're also working on sort of heuristic techniques that will sort of remove some of the uncertainty with selecting arc warping points for the time being. But yeah, that's a great question.
Yep.
Yeah.
Thanks,
you,
Arne. Derek Jones, you had your hand up next. Do you want to
Hey, Devin,
yourself?
good presentation.
Thanks, Eric.
And I don't think that I realized that it was Karina's group who's doing the Cora similarity type stuff. But as you were presenting it, and maybe it's a question for Karina and Vilnius, if we're trying to hit a perfect correlation score, and the data that we're feeding into our ARCGen to create those corridors obviously is pretty disparate. I'm wondering what the actual good value would be, because we're always aiming for 1 on Cora, right?
Mm-hmm.
But if we took any one of those signals there's no way that we're going to get a 1. And so I'm curious if 0.5 is good for this technology, or what's our aim?
I should have looked that up. I can't remember. I read the paper recently. I think the aim is have a model that is qualified. I think it's above 0.5 or 0.6. That's my think. You'd have to double check the standard because it is written in the CP550 technical bulletin. And the reason for that is this is sort of a it's kind of a more rigorous approach than you get in your traditional Cora or BioRank scores. So that's one of the reasons why we have these 2 scores as well. The ellipse score is more of a straightforward copy of the Cora and ISO corridor scores. And the dynamic arc length warping is a bit of a mashup between how the ISO 18571 magnitude score works combined with the corridor score. So it is going to do a little bit more feature alignment. It's going to give you a little bit more of a match to the underlying data, or it's going to stretch things to the underlying data. But you aim for a score as high as possible. So I should say, we have the score of 1 that I highlighted here. Obviously, that's averaged across all points. So your goal is still to have a score as close to 1 as possible. But the actual acceptance value, I think, is lower than that. And I think there are 2 different values for ellipse score and dynamic arc length warping. I'm sorry, I should have actually checked that before I got on the presentation.
No, that's okay. We can have a discussion offline about it, but
Yeah,
I think it will be something we'll need to evangelize to the non-modelers, because everybody is so used to looking for 1. But I think that probably you're not going to be getting that very often with this new technique.
My suspicion is no, but at the same time, we're also, one of the other things compared to sort of the ISO standard or the Cora is that the corridors are actually quite a bit wider with the ellipse technique, because we're actually using standard deviations as opposed to sort of a scaled value based on peak magnitude. So you're trading off on both cases. But absolutely, this is a more complex method. But in my opinion, we're dealing with more complex problems. We need a better way to actually evaluate those techniques.
Yeah, makes sense. Thanks, Devin. See you around.
Absolutely. See See ya.
Johan, I think you're next.
Let's see here. This was not good. So my headset broke
Yeah,
down
we
here
can hear you.
early on. Yeah, but you
I
can
can
hear
hear
me
you, though.
now. Thank you.
Yep,
Yes.
I can hear you.
Good. And see me also with my.
I can't see you, but I can hear you.
You're a bit
Okay,
blurred.
that's fine.
But
That's
that's fine.
No problem. Thank you for the presentation. Nice work.
Thank you.
I have a couple of questions. So I'm
Absolutely.
sneaking in a couple of questions here. The first one being the signal registration and the warping. I thought that your message was that it kind of converged when you add more and more.
It kind of
So
converges, yes. Yeah.
yeah, so my question was really, there's no risk of overfitting if you go for many.
Generally, no. I have observed cases with less behaved data sets where you do get some overfitting.
Mhm.
My recommendation, I think, would be like kind of follow like a stepwise approach, and you kind of converge in that response, but don't go further. Like what I want to caution people against is just putting in like a big number and seeing what happens. Because I have observed in some cases where you do see something that looks like overfitting.
Okay.
It's not common, but it can occur.
Yeah. Okay. Interesting. The second thing here, I'm thinking about the method here for EuroNCAP and the thresholds here and the numbers we took. So the way I see it, I think this is a good first step, but I think what we really should do, as we are planning to use the human body models to include variability, populations, and so on, I think it would make more sense to include the variability in the simulations. So we run some kind of stochastic simulations. And when we compare it to cadaver test, then we would try to represent the variability in the cadaver test. And then we would use your second method here, where we can do a proper statistical test to compare the simulation model with and the variability in
Actually,
this.
I agree completely in that. One of the things that we're working on in the background is trying to extend this new statistical technique to do model validation. And we're investigating a couple of ways internally. I'm not quite ready to share that, I'm afraid, at this point, especially since ArcMap has not actually been published yet. But I agree, like, I don't want to diminish any of the work that Karina Klug's group has been doing here. It's been very difficult to work. And you don't want to make too many rapid steps, like too many steps too fast, I would say. You don't want to sort of leapfrog the community too much. Just the work performed by Karina Klug's group of getting all this initial data, digitizing it, getting it from original sources, is a tremendous contribution to the community. And it will drive a lot more stuff, such as the statistical analysis in the future. But I agree, like, I think there are ways to advance it, but that doesn't diminish the work that Karina Klug and the group at GRAS have done.
No, but then I'm thinking similar to you, how we could extend this in the future then and make a validation that also includes the variability in our simulation model, which
I
we
would love
want
to
to include.
investigate that. I would love to investigate that, and that is on the roadmap. It's just I can't give you a timeline on where on the roadmap that is.
Okay, thank you.
Absolutely. I think there was a comment in the chat.
Yeah, Karan had to leave, so he left a comment before or left a question in the comments before we left, on the chat before we left.
Okay, so this is more so a question about the EuroNCAP stuff. We've seen that these two scores are very sensitive to changes in responses. Even a small change in X changes those two scores significantly. Yeah, this is just, it's early stage work, right? And it will be polished and adopted more as we continue to advance the EuroNCAP findings. I brought this up because it's important to note that it's like applications of ARCGen. And while we have been involved, I've been involved with some of the development of this, it's mainly been spearheaded by Karina Klug at GRAS rather. But yeah, if you have any questions, I can definitely convey them to Karina Klug's group as well. Also, if you're in the chat and you want to learn more about the HBM4VT process, I think there's a general assembly next Wednesday at Well, it's 6 a.m. my time. I don't know what time it is Central European time. So just letting people know.
Yep. That's right. And it's open to anyone interested.
All right.
Good. I don't see anyone else raising their hands. I think that's it. That was really nice to have you, Devin.
Oh, thank you for the invitation, Joe.
Really nice presentation. I should maybe mention something non-technical, very nice animations. And we chatted about this after your Kobe last year, after your presentation.
I'm really proud of the animations, actually. They turned out to be way more work than I thought, but I'm pretty proud of them, and I try to use them as much as I can.
They look really good. And you use Manum software, and that's
Yes, so there's a
one-
Python package called Manum. If you're familiar with the YouTube creator 3 Blue 1 Brown, it's the same software that he does for all his mathematical animations. It's got a learning curve, like steep as Everest, but once you sort of get over it, it's much more an exercise in graphical design. It's actually pretty fun to use.
Yeah, I think it's worth it. It made facilitation fun. Really good.
All right.
Yep. Thanks very much, Devin, and I hope to see you around in one of these conferences soon.
I want to get out. Yeah.
And
right.
Thanks everyone for joining, and have a good day. Bye.
Thank you.
Thank you.
Bye-bye.